Now, heading light, write down heading magnetic force and dot acting on a current carrying loop placed in uniform magnetic. So guys, we are actually seeing what exactly is the magnetic, what exactly is the torque or force experienced by a current carrying loop placed in an external magnetic. So yes guys, everyone can see the magnetic field, right? The magnetic
Yes,
field is
sir.
acting towards right, and let us say I have a rectangular loop ABCD. Okay, sir, why are you choosing a rectangular loop? For simplicity purposes only. Okay, the loop shape may be rectangular, the loop shape may be, this thing triangular, doesn't matter, it may be a random shape or thing, but please remember we are talking for simplicity purposes, we are starting with a rectangle. So let us consider a rectangular loop of length L and breadth B. Please remember this is an important part of your school derivation. Let us consider a rectangular loop A, B, C, D with the dimensions L cross B. Can you see the dimensions L cross B? Shall I write it with length L and breadth B? So loop ABCD carrying a current and let's say the direction of this current is clockwise. The direction of this current is clockwise. Okay? Hello? So let us
Yes,
consider
sir.
rectangular loop carrying a current I. Now, we need to find what is the net force. To find is basically the net force on the whole loop. Okay? So I'll write it in words. The net force acting on. For that, basically, what I will do, I'll try to find what is the force acting on individual this thing, individual parts, and then just add them vectorically, right? The
Yes.
force acting on AB, force acting on BC, force acting on CD, and force acting on DA. Now, see this thing, guys. First of all, can you see here in this case BC and AD? They are the one which are perpendicular, right? Whereas AB and CD, what is the this thing on AB and CD? Can you see AB is perpendicular to B and CD is antiparallel, right? Yes or no?
Mm.
So the force on BC, sorry, the force on AB and CD is zero. Force on AB is zero and force on CD is zero. Why? Because theta is 0 degree and here the theta is 180. Shall I explain a little bit more key you understood by theta 0 and theta 180 degree? Yes? Guys, did everyone understood this?
Understood.
The
Yes.
angle between the length
Yes,
or
sir.
basically the angle between the current vector and the magnetic field is 0 degree. Angle between the current and magnetic field is 180 degree. Now the force on BC and the force on AD. Can you see the angle between length and the current vector is basically 90 degree? Yes. So the force will be maximum. But can you see what will be the force? The force will be B into I into L. And what will be the direction of this force? Yes, can anyone tell me what will be the direction of this force?
BC will be towards the right.
Wrong. BC, it is,
The
current is
force on
going
what?
down, magnetic field is towards the right, so hence the force will be coming out.
We're coming upwards, yeah.
So
Okay.
force on BC will be coming out and force on AD or DA will be going into the plane. So basically this will be coming out of the plane and this will be going into the plane. Yes or no? Yes, guys?
Yes, sir.
So this is basically your example one. From this, can you see over here? What is the net force? Can you see this force and this force is one and the same thing but acting in the opposite direction? So the net force on the loop ABCD is basically FAB plus FBC plus FCD. Shall I write everything again? It's fine. Can
But
you
the
see over
total
here?
force is 0, right?
Huh?
Total force is 0, yeah.
Yes. Yes or no, guys? Sir,
Yeah.
so you cleverly took only this example where this was getting 0. No, take another example. No problem.
Sir, I have a doubt.
Please ask.
The direction of force in AD and BC.
Direction of force and AD and BC. See me. Can you see me? Hello?
Yes, sir.
First of all, current downward direction, L. Right hand downward,
Yes,
put it
sir.
downward. Now can you see the magnetic field is acting towards in this direction from here to here? Towards your right.
Yes, sir.
Towards your right, yes or no?
Yes, sir.
So ऐसे can you see magnetic field की तरफ, and when you do this, your thumb point towards you.
Okay, sir. Yeah, got it.
Similarly, AD,
Yeah, I got it.
है ना? And magnetic field is over there. Okay.
Okay, sir.
Let's take another example. Suppose the same rectangular loop is there, sir. See? And the magnetic field is acting out of the plane, suppose. Sir, in this case, definitely there will be some net force. Yes or no? Is this case and the previous case completely different, right? In one case, I have taken magnetic field into the plane of the paper. In one case, I take magnetic field in magnetic field in the direction perpendicular, and we know perpendicular is the maximum direction. Ayana.
Yeah.
Now again, I have this loop A, B, C, D. Tell me, what should be the direction of current, guys? Clockwise, anti-clockwise? तुम बताओ, मैं वैसा लूँ. Tell me. Let's take it anti-clockwise.
Clockwise.
चलो, clockwise बोला तो मैं clockwise. Let's take it clockwise. So this example. Now, can you give me what is the direction of, again the same thing, FAB, FBC? Can everyone give me the direction? Please start working on it fast.
Yeah.
Can
So
you
for
see the
BC,
magnetic?
it's towards the right.
BC is towards the right. Let me check, and at the same time I'll show you as well. So this is coming. BC is towards left.
Towards left. 1 second.
Magnetic field is coming out
Yeah.
of the.
It's coming out. Yeah, I took it as inwards. My bad.
है So the force acting on BC, guys, please do it with me. See, if you have any doubt in any of the forces direction, please tell me. So the force on BC direction is towards left. है ना? I can write I cap J cap, but I am not writing I cap J cap as of now. Is it fine now?
Yeah, it's fine.
Okay.
Because it's
What
gonna
about
cancel out anyways, right?
yes, CD? Can you see CD? Magnetic field is coming
Yeah.
towards me, and you know the length is
Towards-
going like this. Thumb is pointing up.
Yeah.
Guys, are you doing this with me?
Yes, sir.
Do I need to
Sir.
turn your cameras
Yes,
on
sir.
so that I'll know? Okay, is it fine? Everyone is. I'm assuming everyone is doing the same. No need to be ashamed. You are in your own privacy at your own home. So no need to be ashamed of doing, you know, like this and that. कोई दिक्कत नहीं, it's fine. Okay. Now DA, tell me, what will we see? The current is going upwards.
Towards the right.
Magnetic field
Right,
is like
yeah.
this. So can you see? Is this clear, guys? And the last one, AB will be there. So AB is
Sir, could
downwards.
you show how to do the AD? I mean DA.
DA देखो current ऐसे जा रहा है ऊपर. But when you will do like this, the magnetic field will be pointing into the plane, which I don't want. I want it like this. So can you see magnetic field is now pointing towards me? And when I do this, yes. It's a once more.
Yes, sir.
DA ऊपर. Turn it. Why do I turn it? Because the magnetic field is pointing towards me, and I want to move. I can't move my fingers like this, no? Can I move it my fingers like
Yes,
this?
sir.
Why
No,
not?
sir.
No.
So that's why. So because the
Okay,
magnetic
sir.
field was over here. So
Yes, sir.
like this.
So because everything is mutually perpendicular, I can use the left hand rule, right?
हाँ कर सकते हो, but I told you not to rely on left hand and right
Yeah.
hand rule, है ना?
The left hand rule doesn't work always. I've seen.
Yeah, left hand rule only works when you know you have a
Mutually
magnetic field
perpendicular.
and length perpendicular to each other. Magnetic field and current perpendicular to each other.
Yeah.
FCD is upwards. And now we have decided the direction. Can anyone give me what is the direction? What is the force's magnitude? This thing was having a length L and this thing was having a length B. So can you see FAB and FDCD? This will be BIB. This will be BIB. This will be BIL and this will be BI. So can you see this will cancel out with this? This will cancel out with this. Ultimately, the net force will be 0. Are you getting my point, guys? So can you see in both the cases
Yes,
which we
sir.
have taken, the net force is acting always is 0 node. The total magnetic force acting on a current carrying closed
Closed loop. Sorry, 0.
is always 0.
In a uniform magnetic field, right?
Correct. In a non-uniform magnetic field, it may or may not be equal to 0.
It may produce torque.
What?
So we get the same result when we place an infinite current carrying wire next to it in the vicinity.
No, infinite current carrying wire is basically having what? Can you see the magnetic field due to this wire is basically mu naught by 4 pi into twice of I by R. Can you see this term? With position, the magnetic field intensity decreases.
Yeah.
It's a non-uniform magnetic field. No?
Okay.
You can't do that in case of uniform. You can do this if
Sir?
the loop is very small as compared to wire. Yes.
So even if we like tilt it and place it, then also it will be the same.
And
We
if
get
we
F is equal
tilt
to
it, that implies
like in a
like
particular
BC is
if
coming
now
out of the
place
plane
it
and AD is
in
going into the plane,
right?
right?
No, sir, not like that. Like now the loop is in the plane, right?
Even if the loop is out of the plane, still the force is 0. We'll do that as well. The next thing is that only.
Okay.
Because that will prove that even if the loop is tilted now, the force is 0, but the torque is non-zero. Here in this case, the torque is I cross G. It is maximum in this case as well. No, it is minimum in this case. It's 0. So, Venus and Venus.
So, sir,
Yes.
in moving coil galvanometer, F net is 0, but still we have some certain torque
Torque,
acting
torque.
on like
Yes.
A beam DC.
Yes.
Okay.
So anyways, let's continue with our note. The total magnetic force acting on a current carrying closed loop is always 0 in a uniform magnetic field and is independent of the shape of the loop. Is this clear, guys? So don't think, sir, you explain only for rectangle, so it will be only rectangle. No, not necessary. Any loop. है ना? Is this clear, guys?
Yes, sir.
Yes, sir.
But
Sir,
it
is
may
it necessary that the loop has to be symmetrical?
not necessary at all. Still, F net is 0. Okay? Okay.
Yes, sir.
Yes, sir.
Why? Because whenever it will be like this now, it will have certain components. It will, when you break the small element, and when you do you remember the last time when we did the derivation for random shaped conductor? Random shaped conductor can be assumed as a straight line, yes or no?
Yes, sir.
So basically, whenever a random shaped conductor is there, you can assume this as a straight line. And then once it becomes a straight line, it will become like a loop, this rectangle or square or something like that. है ना? You may do this or not. कर सकते हो नहीं कर सकते?
Yes. Yes, sir.
No. But it may experience certain torque when the loop is not aligned with the magnet. Is this clear, guys? Is this clear?
Yes.
Yes.
Heading likho, please. Write down the next heading. What's the time now? What lot of time. Torque due to magnetic forces on so guys, basically we are saying what is the torque due to magnetic forces in a on a current carrying loop, है ना guys? Shall I need to write that?
No, sir.
Current carrying loop. So everyone can see this magnetic field, right? Everyone can see this magnetic field, right?
Yes.
When I see the
Yes,
front view, it looks like this. How will I draw it? Let me draw it like this. Guys, please draw the diagram very carefully. I am drawing it carefully so that at least you can understand what I am drawing exactly. So basically, guys, can you see a loop? Is everyone able to see a loop?
Yeah.
This is the axis of the loop. This is your A, B, C, D. The area vector of this loop, everyone knows the area vector, right? I think area vector we already talked in electric flux when we discussed. So the area vector is always perpendicular to the loop. Yes or no? Everyone knows area vector is perpendicular to this thing, right?
Yes.
Okay. Let's say the current is going in again clockwise direction. Okay. So the front view looks like this. This loop is a little bit tilted. Okay. Let's say the loop is tilted in such a way that the area vector is making an angle of theta with the magnetic field. Please remember, this diagram may not be that much clear. So for making it clear, go to the top of this thing and observe from here. Guys, please observe from here. This should be your eye. Observe from here, yes or no? Guys, will you be able to observe from here? Hello? No one is saying anything?
Yes, sir.
Yes, sir.
Huh? Observe from here. When you will observe from here, will you be observing any change in the direction of magnetic field? No, right? So the direction of magnetic field will still be the same. Control C, Control V, Control V, Control. Now, when you will be seeing from the top, what you will be seeing, you will be just seeing of the wire AB. Will you be seeing only the wire AB, which is at an angle theta? Yes or no?
Yes, sir.
So basically, you will be seeing only this wire AB, and the current in the wire will be going from A to B. The current in the wire from D to A is coming out of the plane. Can you see? The current is coming from D to A, and since you are looking from the top, so what will happen? So you will observe that the current in that wire is coming like this. The current over here is going like this. The current in B will be going into the plane, and there will be CD which you will be not able to see, right? What will be the direction of current in CD? It will be from C to D, right? Yes or no, guys?
Yeah. Yes.
Now suppose if I want the area vector, let me delete it and draw it with a different color. I am drawing all this with a different color so that you people can understand it well. Okay, so this is your area vector. So basically the area vector will be perpendicular to this loop, right? Why are you not able to see the whole loop, guys? Because the loop is into the plane, and since you are observing from top, so you will not be able to see the whole loop because the loop is beneath this thing. So this is the area vector, and can you see over here, I rotated in such a way that the area vector is making an angle of theta with the magnetic field. Is this clear, everyone?
Yes, sir.
So basically this is your loop. We have tilted the loop such that angle between area vector and loop and magnetic field is with how much? Theta. Now, can you please tell me what will be the direction of forces acting on this? What will be the direction of force acting on AB? Can you see AB is acting downwards? Anji, guys, please can you tell me, achha, what is the length of this? Hello? Guys, what is the length of this? This
L.
length is L
L.
and this
B.
length is B. So basically the wire AB which you are seeing is of length B, okay? So
B.
AB is equal to So now see this thing over here, guys. What is the force on AB? What is the force on AB? Can you tell
Upward.
me what will be the force on AB?
Upward.
A is like this. A, I is going in that plane. I is going like downwards, and B is going to the force on AB is acting in the upward direction. I'll draw the forces with green. So the force on AB is acting in the upward direction. Whereas what will be the force on CD, guys? The force on CD will act in the downward direction, right? I'm
Yes, sir.
drawing this force over there so that at least we should not get confused. Right? So force on AB is acting in the upward direction, and force on CD is acting in the. Let me check it once again. Current is this, force is this. Correct. And similarly, the force on CD is acting like this. Yes or no, guys? I think force on AB and force on CD is pretty much clear to everyone. What will be the length of, what will be the value of this force? FAB will be equals to B into I into, and what is the angle between length and this thing? The length vector and the B vector, the angle between will be 90 minus theta. So this force will be BIL into sine of 90 minus theta. The same thing will go over here, BI into what is the length of AB? Length of AB into sine of 90 minus. So can you see, guys, the force is these two forces which are acting in the vertical direction will cancel out each other. Yes? Yes or no?
Yeah. Yeah.
They will cancel out each other. What about the forces which are acting on AD and BC? What about the forces which are acting on AD and BC? Can you see AD? The wire is going up. The magnetic field is going towards right. So the angle between them is how much? 90 degree. Yes or no? The angle between the wire and the magnetic field will be 90 degrees. So what will be the force acting on it? The magnitude of force will be B into I into L, right?
Yeah.
But what will be the direction? That is important. Direction, tell me, please.
Okay.
So will it be into the plane?
Inwards, yeah.
The force here, are you talking about here?
Yeah.
Yes.
Yeah.
For
The
AD.
force on AD will be into the plane, and similarly the force on BC will be coming out of the plane. When we
Yeah.
will draw these forces over here, the force on AD will look like this, and the force on BC will look like this. This will be
So this will be producing the torque.
this two forces will be producing the torque. Okay. Current is like this, magnetic field like this, hence the force is like this. I think everyone it is pretty much clear, right? Is
Yes,
it
sir.
clear? Is there any doubt to
Yes,
anyone?
sir.
This is the direction of magnetic field. This is the direction of current. So you can either apply, if you feel like Fleming's left hand rule will be easy on this, go for it. I don't mind. Okay.
Okay, sir.
So this will be the length and this will be the direction of current. This will be magnetic field. Hence the force acting on it. You can either give the direction of FAB and FBC. Direction can be given using Fleming's left hand. If you want, then only do it. Otherwise, don't do it. मेरे हिसाब से तो don't follow. So is this clear, guys? Now can you see over here the force on AD? Force on AB is basically negative of force on CD. Yes or no?
Yes.
So basically
Yeah.
they cancel out. And similarly, force on BC and force on D. Again, they are negative vector of each other, so they cancel out. Yes or no? Are you getting my point? So what? That's why the net force is how much? 0. So Ovia, is your doubt clear now? Ki what will happen if the loop is placed a little bit tilted? Will the force be
Yes,
0?
sir.
Yes. Again, the force will be 0. But what about the torque? F net was 0, but net torque is non-zero. Okay, so let's find it out. Now can you see over here, guys? I'll draw the diagram. I'll not draw the whole, just I'll just draw the things which are necessary. Okay. Why am I copying the whole thing? I'll draw the new diagram. So now we are doing torque. Okay.
Okay.
So guys, this is your AB wire. The current. The length of AB. And what is the direction of forces on CD and this thing? Was this the direction of force on BC and force on D? Yes or no,
sir.
guys?
Yep.
The magnitude of force on BC and the magnitude of force on DA were both equal and it is equals to BIN. The magnitude of force on DA and sorry, will not write the F, AB and FBC will not be producing any torque because they are acting in the opposite direction, but their perpendicular distances but FDA and FBC will be producing a torque.
Hmm.
So what will be the torque as they form a couple? So can you see, guys, two equal and opposite forces in the opposite direction? So we know the formula from 11th grade: torque due to a couple is basically what? Magnitude of one force multiplied by the perpendicular distance between both the forces,
Hmm.
right? We know this thing,
Yeah.
right? From 9th,
Yeah.
11th. So can you see, guys, if I see this is the direction of FDA produced. So can you see the perpendicular distance between the two forces will be? What will be the perpendicular distance between the two forces? Will this be the perpendicular distance? Let's say this is C. Here,
B sine theta.
yes, perfect. Now, how will we find out the value of BC? What is the length of AB? Length of AB is B, and please
B.
remember the area vector. According to the area vector, was this the area vector? Yes. Yes or no?
Yeah.
The area vector was having an angle theta. So let me form this here. The area vector is forming an angle theta. So if this angle is theta, this angle is 90 minus theta. Yes?
Yeah.
Yeah.
This angle is 90 minus theta, then this angle is 90 minus theta. Yes? Alternate integers.
Yeah.
And if this
Yeah.
is 90
Yeah.
minus theta, then this should be theta because this is 90. Are you getting my point, guys? If this angle is theta, then this angle is theta. Clear? So I'll write it directly. This angle is theta, this is B, hence BC. I is 10 multiplied by BC. And BC is nothing but. Hey guys, let's not name it as C. Let's name it as O. Okay? Hello guys, let's name it as O. Why? Because C is the point on the loop, right?
Yes, yes, I did.
Yes.
This will be D, this will be theta, hence O B will be equals to A B sine theta, which is B sine theta. So I'll write this as B into I N sine theta. And can you see the length into breadth become what?
Area.
Area. So this is your torque acting on the loop. If a loop has n turns, then torque is equals to bi into n or है ना? So b na sin theta. So this is the value of torque. Okay. Please remember this
Yeah.
is just the magnitude. How will we give the direction? Direction
Cross
will be
product.
given by in vector form.
Mm.
Can you see guys? B I N A sine theta. What else is a scalar quantity? Can you see? This n is a scalar quantity, I is a scalar quantity. But area can be taken
Yeah.
as a vector quantity, right?
Yes, sir.
Yeah.
So basically in vector form, the same formula is written like this. I is equals torque is equals to I into N outside, and this will be A cross. Is this clear?
Yes, sir.
I into N A cross B. Always remember, see guys, एक प्यारी सी चीज I think you people might have noticed. For every force acting on a moving charge, it was equals to what? Force acting on a moving charge. It was Q into V cross B. Force acting on a current carrying conductor, it was I multiplied by
BIL.
B I
and
N
even
sine.
the
Yeah.
torque is I into N into A cross B. What is the only thing which you notice common in all of them?
Cross product. Nothing.
Cross
Cross
B.
product is there, but B is coming at the end.
Mm.
So always, if you
Yeah.
ever get confused in this, always remember the B will be coming at the end.
Yeah. Okay.
So the force component always comes at the end, because in torque in the rotation also it became like R cross F here.
Yes, it is. It did. ठीक है? So कुछ small things you need to notice. अच्छा. Note. This is clear. I think I into N into A cross B is clear pretty much. Right?
Yeah.
I can write this torque as I into N into A vector. Since this part is scalar, no? I can multiply it with A vector cross B. This thing, I'm naming it as M. Okay?
Oh, magnetic moment. Right. Mm.
We can write torque vector like this, M vector, where M vector is called as magnetic moment. Guys, do you
So
remember?
for any figure,
For any figure.
magnetic moment NIA.
मतलब at least for circular loop, circular current carrying loop. For circular
So
current.
if the loop is in shape of like a circle also, it's fine?
It's fine. Doesn't matter.
Okay.
Magnetic moment for a current carrying loop.
So I have a doubt.
Bolo.
The magnitude of torque includes the term sine theta, right?
Yes.
So why didn't we include cos theta in the magnitude of force?
Where?
Why there should be cos theta, right?
Where? I'm asking where it should be cos theta.
On the sides, like you've written before this. Yes, sir, here. You've written magnitude is BIL. So it should include a cos theta, right?
Here. यहाँ पे. This thing should include a
like
cos
in
theta.
blue, written in blue. The magnitude of SBC and.
कहाँ पे? Shall I go up or down?
Sir, here. In the note.
Here?
So, yes.
So in the note. Yeah.
So here, where did I write force?
Sir,
This
in the
was called-
note that. Not this, the note written
So
in
the
blue.
blue colored note.
So can you scroll up?
Just tell me where to stop, okay?
Yeah.
Here?
Here.
Yeah,
Yes.
here.
These
Should it include the term cos theta?
were here, in torque couple here.
No, the magnitude of force on BC and magnitude of force on DA sides. We've written it as BIL.
It will have sine 90 minus theta, no? Can you see? B into I into L into sine 90 minus theta. What is sine 90 minus theta? Cos theta only. But can you see that?
Why haven't we included that term, cos theta?
Why haven't we included that term in calculating the torque?
Force. In calculating the force itself. Like in magnitude of torque, we include the term sine theta. So here we need to include cos theta, right?
But the point is, can you see over here, FAB is acting, FAB is in the upward direction, FCD is in the downward direction. And both the forces were equal, BIL cos theta, BIL cos theta. So can you see, even if both the forces were equal, so that's why these two, AB and CD, were cancelling out each other. Similarly, they too were also cancelling out each other, hence the net force was equal. But when we were discussing about torque, that force which is acting on AB and that force will be acting on BC will not be producing any torque. Why it will be not producing any torque? Can you see both these forces are acting in the opposite direction, which is first condition, but they don't have any perpendicular distance between them. So that's why we didn't include these two forces. This force and this force were not included. But these two forces, FAD and FBC, they had certain perpendicular distance between them, which is basically this from here to here. So that's why these two forces, we had to include the perpendicular distance. Since these two forces were not having producing any torque, so when we were calculating torque, we didn't include these two forces. That's why the cos component didn't appear. This was your question, right?
Yes, sir. Why didn't it include cos theta?
So the question should be, why didn't we include these two forces? We didn't include these two forces because they didn't have any perpendicular distance between them. Now suppose you are this loop, and I tell someone to pull from your head up and someone to pull your leg down. Will you be rotating?
No.
Exactly what is happening to this loop. But suppose if someone applies a force on your right shoulder to the back of the paper and your left shoulder front of the paper, will you rotate about your head?
Yes.
That is what is happening. Okay. Now you understood why there was no torque due to FAB and FCD?
Yes, sir.
Okay. Since there was no torque, that's why these forces were not included. It was not because cos was not involved. No, these forces only were not involved. Okay. Anyways, Now, when I write the term torque is equal to bina sine theta, I can write it in the form of I into n into a cross b. Since I and n are scalar quantity, I can multiply this with a vector and I can make a new vector out of it. When I multiply I and n with a vector, I got magnetic moment for a current carrying loop. Magnetic moment is I into n into a. Please remember the direction is same as the area vector. The direction is same as area vector, whereas the magnitude is I into n times. I into n times of area vector. Is this clear? Is this clear,
Yes,
guys?
sir.
Please
Yep.
remember the direction of area vector. Also note. The second note is this. The direction of area vector is given with right hand thumb rule on the direction of current in the loop. So suppose guys, if you have a current carrying conductor like this, and let's say the current carrying is in the direction this one. So can you tell me what will be the direction of area vector? What will be the direction of area vector? Will it be coming out of the plane or going into the plane? Tell me. Guys, please tell me. The direction of the current will, the direction of the area vector, will it be perpendicular to the plane or will it be into the plane? अरे बोलो यार.
Sir, could you repeat your question?
My question is, if the direction of current is mentioned in these two loops, A, B. Here the current is flowing anti-clockwise. Here the current is flowing clockwise. So can anyone tell me what is the direction of area vector in these two cases?
So
So the
for
first
first
one is
is out
upwards.
of plane.
It will be out
Yeah.
of plane in the first case, and it will be
It'll be
Into
inwards.
plane.
to the plane in the second case. Yes or no, guys?
Yeah.
Area vector is out of the plane and area vector is into the plane. Is this clear?
Yes, sir.
Please
Yes, sir.
remember, whatever be the direction of area vector, the same magnetic moment vector will also have the same direction. Is this clear? Any doubt in this, guys? And just once you
No,
find out
sir.
the direction of M, now give M cross B. Please remember, you don't need to find out the direction of a torque. Note, एक और note. Generally, we don't require the direction of angular quantities. We require only the sense of those quantities. Sense, you understand that, guys? Please
Yes,
remember,
sir.
sense of
Clockwise
those
and
quantities given by direction of curling of the fingers. When you curl, no, whenever in A cross B, you curl your fingers from A cross B, right? So see where your fingers are curling. Are they curling in clockwise direction or are they curling in anti-clockwise direction? When they are curling in this thing, you will get this as the sense. Please remember, whenever someone says what is the sense of any angular quantity, that implies anti-clockwise or clockwise. Yes or no?
yes, sir.
Okay. So I think this is pretty much clear to everyone. And now we'll do the special cases of this, and we'll end up the class after this. Okay. I'll leave 5 minutes.
So can you plane for a circular loop?
Can you do for what?
Circular loop.
The circular loop. Now, what's the problem? Tell me. Let's draw a circular loop. हाँ भाई बोलो सर्कुलर लूप क्या करूँ उसके बाद?
So here the force will not be zero, yeah, because we find the force by integration of dl.
Here also the force will be zero. पूछ कैसे?
How?
Let's say the magnetic field is in what direction? Let's say the magnetic field is
Into the
like this.
point.
Okay.
Okay.
एक यहाँ पे एक छोटा सा small vector ले. Will this be your dl vector?
Yeah.
Yes.
With dl vector will be having two components, dl parallel and dl perpendicular.
Yes.
Tell me what is the force on dl parallel?
No force.
Exactly. So force on dl parallel will be equals to b into I into dl parallel into what is the angle? Sine 0. So that's why this
Zero.
force is
Zero.
0. The parallel component of the force is 0. है ना? But
Yeah.
ये वाली force दिख रहा है? dl perpendicular. This will be F into dl perpendicular. Sorry, this is parallel. So b into I into dl perpendicular sine of 90 degree. Yes or no? So
Okay.
this will be b into I into dl perpendicular. But sir ये तो zero हुआ ही नहीं. होगा? कैसे नहीं
But you
होगा?
cancel out with the other components here.
ना. Basically जब तू dl vector को integrate करे, from where to where will you integrate? You will integrate from here to the whole circle, right?
0 to 2 pi r.
You see, you will integrate only the y component. So basically, you will be going up
Oh,
first.
integrate from 2
और
r.
फिर यहाँ से वापस से यहीं पे आ जाएगी. So basically, this whole length will become zero from here to here. Throughout the circle, when we talk about this whole length will become zero. So ये पूरा
Wait,
zero
sir,
आ
could you
जाएगा.
explain again?
When this dl vector perpendicular component you are taking. You're taking
Yeah.
this component now. So basically this won't be a circular loop anymore. It will be just a wire which goes like this, then like this, and comes back to like this. Are you getting my point, guys? So basically, what is the overall length of this wire? Is there
Zero.
overall length? Zero, no. So this thing will become zero. So can you see? Parallel se bhi zero, perpendicular se bhi zero.
So it's basically wrong to take a element dl and just integrate for 2 pi r.
हाँ बेटा कभी if I would have taken dl vector, if this dl vector, ये देख रहा है ये वाला, if I would have not broken it into two components, and if at every point, for example, suppose I have a region, अच्छा this is the reason for circular, there is a circular electric field also. वो अपन बाद में चर्चा करेंगे कि कोई dl vector एडवांस में मिलेगा. If suppose by case I produce a magnetic field which is parallel to dl vector at every direction, then when you will calculate the force on this wire, you will do b into I into dl vector. And can you see, for every element over here, the angle was 0 degree. So then you will write sine 0. Are you getting my point?
Okay.
Yes, sir.
If your magnetic field vector was perpendicular at every point, then you would have written 90 degree. Are you
90.
getting my point? If this dl vector would have same with the direction of magnetic field vector would have been same for every element, then you would have generalized it for the whole loop. No? Then the dl vector integration should be 2 pi r. थोड़ा सा little bit complex maths is there, but please समझो.
So,
हाँ.
can you explain how the perpendicular thing becomes zero again? I don't understand that.
Shall we move back to the previous lecture?
So again, you will explain this by the displacement thing, right?
You can say. Do you remember this? Why did the y component become 0? Guys, do you remember why did the y component become 0? What is happening? See, it is going back to the same place, right? So guys, if you remember in the last class, we took like this dx was basically the, why did we make this random shaped wire as a straight line wire? Because one component was giving 0, which we know. And do you remember when you integrated this component, the one component which was perpendicular? So do you remember you integrated it from 0 to 0? Why did you integrate it from 0 to 0? Because the first element was over here with the y coordinate 0, and the last element was also having the y coordinate 0, right?
Okay, so having the same point. Yes, sir.
So the same logic can be applied over here.
First point to the last point is
The
equal to
first
that.
is suppose if I chose this as the y-axis, if I chose this as the point where everything is starting, this as the point. So this is my, so can you see the first element will also have what? The 0, and the last element will be also on 0. So it will be integrated from 0 to 0.
Oh, okay, sir.
Yeah? So that's the case. Samanya and Mridul, any
Okay,
doubt?
sir.
Everyone else also understood? Sir, even if it's circular, doesn't matter.
Yeah.
Yes, sir.
Yes, sir.
So in the second case here, which we drew,
Yeah, tell it.
so
Shall I delete this?
second case which you have drawn, no, whatever we drew right now, yeah, for the second case,
This one?
yeah. How is the magnetic field here?
Magnetic field, I'm giving you an example. If the magnetic field is like parallel to this particular thing, or if the magnetic field is perpendicular to this, so then can you see for every element, this dl vector and this perpendicular or parallel, whatever it is, then you can use either sine 0 or sine 90 accordingly. It should be common
Okay.
for the whole elements on the loop. It should be not like only one element which is common and the rest everything is one.
Okay.
So anyways, my conceptual knowledge regarding integration and differentiation is good. My basics are strong. First chapter 11th grade. And that is what I advise you people also. So beta, at least differentiation, integration, do it very well. But nobody takes me seriously.
So I just had a conceptual doubt there.
I know. Special case number 1. If theta is 0, guys, please remember, if theta is 0, that implies the angle between, and by the way, the remaining case I'll give as a homework, between area vector and magnetic field vector is 0. Whenever this thing will happen, area vector and magnetic field vector will be 0 degree, that implies if this is the magnetic field, hello people.
Yes, sir.
So if this is the case when the magnetic theta is 0, then can you see in this case the magnetic field is also like this, and even the area vector is also like this. In this particular case, what will be the magnitude of torque acting on the loop? Can you see here? The loop is when the loop when the loop is perpendicular to the magnetic field, then your area vector and magnetic field vector will be, the angle between them will be 0. In this case, the torque acting on it will be 0. Yes or no? Is this clear, guys? What shall be the direction of current for the area vector to point in this direction? The current should go like this.
Anti-clockwise, right?
Anti-clockwise as
No.
seen from right.
Okay.
Oh, sorry, as seen from left. No, sorry. as seen from right. Yes. Anti-clockwise as seen from right, and clockwise seen from left. Yes or no?
Yes, sir.
Special case 2 homework for you people. And special case 3, if theta is 90 degree, angle between
A
area
vector and B
vector
vector.
and magnetic field is 90 degree. That implies loop is aligned along the magnetic. So the last case is basically this. When the loop is aligned along the magnetic field, can you see the loop is in the direction, lying in the direction of magnetic field? When it is like this, then the area vector will be pointing what should be the direction of area vector, clockwise or into the plane or coming or out of the plane?
Into the plane.
Into the plane, because it is clockwise, so the area vector is acting into the plane. Yes or no? If area vector is acting into the plane, magnetic field is here. So what is the angle between them, guys? Here, can you see the angle between them is 90 degree? Yes or no? In this case, the torque acting on it is maximum, and is equals to
Maximum.
E to I into N. It is equals to this, or you can write as it is equals to N. Is this clear? I think our
Yes, sir.
special cases are pretty much clear. In the next class, we'll do moving coil galvanometer, some more questions, some more concepts, and a little bit more questions. And this chapter will be over. There is something advanced concept which is called as Q by 2n cases, which we will do later. We'll write a heading named Q by 2n cases.
Okay, sir.
So, in the next class, we'll be done with MEC and we'll start with electromagnetic induction. And I told you already this thing, guys, the magnetism and matter chapter, and electromagnetic waves. If possible, we'll have some more classes in August.
Yeah.
So
could you
what
please
was that
repeat that chapter?
advanced?
The advanced portion was basically Q by 2m cases.
Q by 2m L वो वाला?
L is equals to Q by 2m. L is equals to Q by 2m. Do you remember those? Do you know these cases?
No, it's mu is equals to Q by 2m
M by
L.
the ratio of the
Magnetic moment and the angular momentum.
Angular
is equals to
momentum.
Q by
Yeah.
2m. ये वाले cases. Do you have those cases in school?
No.
Yeah? How do you
No,
know it?
sir.
I just read it
JE
somewhere.
level notes, sir, online.
Oh my God.
No, actually, I was just doing HC Verma there, the last two questions.
So those are Q by 2m cases. So go advanced portion. It's a pure advanced. So we'll skip them for now. We'll do them later. I told you
That comes with the Bohr model, right?
what?
That comes with the Bohr model.
Yes. We'll discuss them later. That is when we discuss them later on. So anyways, thank you very much, guys. We'll
Okay,
see
sir.
you again in the next class.